this, what I want to open with today, just kind of briefly, is to review what we've got available in terms of getting started with Catapult in the TAC environment. For those of you that already have requested access and have a TAC account, you've seen this. We send this out. We send this out to folks once they have made an application and we have assigned a node in the Catapult environment to you. And so what this contains is some useful information about getting started in the research system that is Catapult down at the Texas Advanced Computing Center, which is what TAC stands for. What we've got down there, system specification wise, so you can see, we've currently got 384 machines down there in 16 racks. Currently, we've got a chassis, currently we've got these are divided into 4 different chassis. The racks are 48 server pods. Currently we have one full rack, 48 servers that are set up that we can use and allow for now multi-node assignments, which is a relatively recent development for us. We will very shortly have a second 48 up and ready to go. So if your research leans that way, we can provide a 2, 4, or 8 node configuration over a Taurus network. To get access, we ask that you send to us your TAC account information, a proposal, and your Altera account information, so that we can then proceed with providing access to everyone. This information is also available on our website under the Apply page. The other thing with accessing down at TAC, you do have to have we do have multi-factor authentication. There is an app for that that can be downloaded from the App Store or from the TAC user portal. Real easy to use and allows you to, it gives you that random number that you need to access your machine. Pointing out too that if you are not in the United States or do not have a US phone number, you do have to use the app, though there is a SMS method available if you prefer that. But we prefer that you work through the app, and it's pretty easy and simple to use. So this is, if you haven't seen it before, this is what your login screen looks like, where it asks for your TAC credentials, your password, and then the multi-factor PIN. And again, just to give you an idea of where things are, if you haven't been onto the environment before, there's a machine. Then once you're logged into your node, you can navigate to, there's a public folder on our CAT data machine. So from your individual node, you can RDP over to the CAT data/publish folder, where you'll find all the publicly available files that are needed in the software development toolkit. You can see there, probably need to update this. We are up at version 1.2 at this point, and you can access all of these files here and download them to your individual nodes. Here we RDP into your servers. The address that you'll use is a combination of your node number, which I assign to you, with production.tac.utexas.edu. And you do have to make sure that you include production in front of your username when you do log in. If you haven't done this before, you're not familiar with this, we get a lot of people that kind of trip up on that a little bit. So you do have to make sure that you include that when you RDP to your machine. Now, I'm not going to go through and read all this, and if you want a copy of this Getting Started guide, feel free to email me and I will send it out. But again, we do send this with all account applications, so that you can then work through, get your access. We cover running the Hello World programs. We outline the folders that are in the SDK, and we do suggest that you read through this prior to accessing and really getting started in your node. We run through setting up the Altera Cortex 2 15.1 version, synthesizing the example FPGA projects, generating the flash memory programming file, programming the FPGA, loopback stress tests, more Hello World applications, and manual RPD file generation. So that, in a nutshell, is our Getting Started guide. Any questions from anyone on this at this point? Okay. Ray, if you're ready, I'll turn it over to you and we can get into the meat of the presentation this morning.
Okay. Can you see my slides? Yes?
Yes, we're good to go.
Okay. So today I'm going to introduce the software APIs. And remember last week we talked about the interfaces we can access in the role. And PCIe DMA and PCIe registers provide the communication between the whole CPU and FPGA. And we have talked about how to handle the incoming CPU signals on the FPGA side. And today I would like to talk about how to write a host program to communicate with the FPGA. So first, here's an overview of the hierarchy. And the driver sitting in the kernel space handles the raw signals with FPGA. And an FPGA communication library, which is called FPGA corelib.dll, provides the interfaces with drivers and exposes the software APIs to the user. And we will focus on these software APIs today. There is also another management library, which provides some API for monitoring and reconfiguration. And users need administrative privileges to use these APIs. So first, before communication with the FPGA, we need to create a handle. So this handle will be passed to all the functions that we will use later. The FPGA create handle function initiates and returns a handle to an FPGA device. The end pointer number should be set to 0. And the flag argument is reserved for permits additional options for future use. So it's currently should also be set to 0. And the last two arguments are point to files that are used to perform version checking. So the PCH version definitions file defines which version registers to verify. And currently it should be set to no as default. And the PCH version manifest file defines the compatible values for version registers, and default is also set to no. And the FPGA close handle release and closes the FPGA handle. So these functions are intended to be multi-process safe. It should only be called once and be shared among multiple threads. So when these two functions are invoked, in the background, there are three things happening. The first thing is the base address register is mapped to the CPU's memory space. Then a pre-pinged physically contiguous memory is allocated, and the physical address are sent to the FPGA. Then an interrupt service routine is registered for the FPGA. Okay, remember last week we had talked about the slot-based PCIe DMA interface, which is the primary method of data transfer between FPGA and the CPU. So what did it look like in the host program? There are several software APIs that manage it. First is the FPGA get input buffer pointer, and the FPGA get output buffer pointer. Last week we talked about that the input and output buffer sits in the kernel pin memory space. These two functions map the DMA buffers into the user space so that software applications can use them. The PD word here is a pointer to the D word. So the PD word star is a pointer to the pointer. So given the handle and input slot number, it retrieves a user mapped pointer to the input buffer for the slot. And the available buffer capacity is finite and should be queried using the FPGA get buffer size, which is another API. The total number of buffers available can be queried using FPGA get number of buffers. You can refer to the user guide for more details or other APIs. So then, once you have retrieved the pointer to input buffer, you can determine its status using the FPGA get input buffer full. It provides a read-only access to the relevant parts of the CPU control buffer. Then FPGA send input buffer initiates a send operation that transfers the contents of a specified input slot buffer to the FPGA. This function is non-blocking, and it returns immediately to the user. The user must specify whether an interrupt should be generated when the message is written to the corresponding output buffer, or use polling. So the driver supports both polling and interrupt. Polling results in higher performance, but it significantly increases the CPU utilization. Now note that the input buffer data should only be modified when the input buffer is empty. So if you wish to send more data to the same slot, you must first wait for the FPGA to finish consuming data by calling the FPGA get input buffer full. So the output buffer is similar. Get output buffer done checks whether the FPGA has written to an output buffer and is available for the host to read. The FPGA wait output buffer is different from the send send input buffer, it will block the calling thread until a message is received from the FPGA for a given output slot buffer. The user must specify whether an interrupt is expected or polling should be used. If an interrupt is expected, a previous interrupt-enabled call to the FPGA send input buffer must have been made to the same corresponding input buffer. I mean, you should set use interrupt here. Then you can use interrupt here. So the timeout parameter, when overridden from the default, will cause the calling thread to unblock before a specified duration in seconds. To disable the timeout, you just set it to 0. And the FPGA discard output buffer allows the user to discard an output buffer after its contents have already been consumed and are no longer needed. Every time when user have finished consuming the data in the output buffer, you should invoke this to discard the buffer for future use. So here is an example. This is the typical process of communicating with FPGA. First, we create a FPGA handle. Then we get the kernel pin buffer pointers. Since the pointers have been mapped to user space, we can now put the send data to the input buffer. In this example, we write random data to the input buffer. Then we invoke the send input buffer to start the transferring process. This function will return immediately. And we use wait output buffer to wait for the FPGA to send data back, and it will block the thread until the returned data is available. Note that we use interrupt here, so it does not consume the CPU resource while waiting. The returned data in output buffer is in output buffer, and we can consume it directly. We should discard the output buffer after the results are consumed so that the buffer can be reused. If all work is done, we should close the handle. Okay. In addition to the DMA engine, we have talked about the simple register-based communication between the software and the row, which is designed for the low bandwidth operations, like performance counters, config row parameters, or start-stop test. So on software, it turns out that it's also very simple to use. Many software visible PCIe memory mapped registers are accessible through PCIe-based address register offsets. And we divide the register space into 3 categories: the shared registers, internal PCIe registers for DMAs, and the user-defined soft registers. Here, shared registers are defined by Microsoft and usually have special meaning, while the soft registers are customized and its usage are totally up to users. So to read the soft register, we simply invoke the FPGA read soft register and provide a handle and the address and the pointer to the return value. To write the software register, you also provide the handle, the right address, and the right value. Similarly, the share register is in the same way. So note that each access to the share register or soft register is atomic, and therefore thread safe. However, a series of accesses is not atomic. There are some special share registers that worth mentioned, which is critical if you want to enable the serialized 3 feature. So to enable the serialized 3 lane of a specific direction, you have to set the corresponding bit on the share register 5. The FPGA share register interface can only read and write 4 32-bit register values. So to set a specific bit, you must perform a read modify write on the share register, meaning that you have first read it, modify it, and then write it. The users can assign an 8-bit node ID value to each machine, initialized to all ones on FPGA reconfig, which can be read to determine the machine names in each serialized 3 direction. The results are valid only if serialized 3 is enabled on both the Catapult board and its neighbor. So share register 5 looks like this. The low 8 bits are the node ID of the board, and 16 to 19 is indicates whether each lane is enabled on this board. And share register 97 contains the serialized 3 neighbor node IDs in each direction. So it looks like this. For each 8-bit indicates the node ID of each neighbor. Share register 96 returns the overall serialized 3 link status for each direction. It is mapped to the 0 to 3 bit of this register. Okay, so as we have discussed in the architecture section, multi-threading is required for high PCIe throughput. So we provide a job dispatch library, which wraps up the low-level functions as I introduced before. It simplifies the PCIe interface while transparently spawns and manages the spreads. Users only need to invoke the send job to send data and receive job to wait for the return values. And both functions are multi-process safe. A job here is an independent task to be completed on FPGA, consisting of send 1 input slot of data and receiving 1 output slot of data. Each job cannot send or receive more than 64 kilobytes of data. It should fit 1 slot. The users can create parallel threads invoking send job at the same send job and receive job at the same time. Then the dispatcher will manage the rest of the work. It basically generates a dedicated dispatch thread for each slot. Each thread waits for data to send. Once data arrives via the send job function, the thread sends the data to FPGA through its assigned slot, and then waits for the output data from FPGA to arrive. And on arrival, the thread buffers the data in a separate queue and frees the slot, making the data available via receive job. To use it, it's also very simple. You just need to create a dispatcher, and it will run in the background. When you need to send or receive job, you just need to invoke the send job and provide a input pointer and output pointer, the size. The library is totally optional. You are free to directly use the APIs introduced previously or implement your own dispatcher. Here is an example of the single thread version of using the dispatcher. The outermost loop is the jobs you want to perform each slot. Then you iterate through the slots and send 1 job for each slot. Then you wait for the output of each slot, and then do the same thing for the next job of each slot. Here's a parallel version. By invoking the parallel for, you create a thread for each slot, and a thread is dedicated to send and receive for each slot, so that you can send and receive data on different slots concurrently. Okay, we also provide a coding framework that simulates a simple row alongside the software program. It can help you to fix simple bugs quickly, but it is modeled in behavior. The software register, DRAM, and the PCIe are modeled in behavior without considering the latency and bandwidth. And the serialized 3 is not modeled, so it can only help you fix simple bugs, but it cannot substitute the real simulation. And you can refer to the user guide to see how to use it. It's actually nothing but run a script. So then I will explain how the coding framework works. The model theme, first the model theme simulates the theme top. Theme top is a specialized top-level file for simulation. It's basically initialize the code and instantiate the simple row, and it has a C DPI hook which connects the simple row system Verilog file to the C interface. During the initialization, the theme top will call initial harness within the harness, which initialize the concurrent FPGA state data structure containing all simulated FPGA DRAM states, PCIe slot states, and the message passing buffers. And next, the theme top will launch the software program in a separate thread, overriding the arguments of the main function with the past simulation command line parameters. The simulation runs until the software program exists. Then the hardware, at this point, the harness will set a bit notifying the theme top that simulation has been completed, so the theme top can call finish. So number 4 is the software program. For example, the provided loopback stress test is compiled with defined code theme 1. Then the program runs and calls the API call as usual without further modifications. These API calls are redefined in the FPGA core lib code theme, which interacts with the simulated Catapult FPGA state instead of the Catapult hardware board through the drivers. And the FPGA state data structure is accessed concurrently by the software program through the FPGA core lib code theme, and by simple row through the test harness. It contains all Catapult interface architectural state, including arrays containing both channels of DRAM data, and the PCIe input and output slots with 4 and dumb bits, and the software register pending request and response. These are all simulated in the FPGA state. And to access the state, theme top services the simple row requests and responses, providing necessary hooks to see DPI calls in the test harness. Each cycle, the theme top will check to see if incoming data is available through PCIe, enqueuing to the simple row if space permits. Similarly, the theme top will check every cycle to see if outgoing PCIe data is available. If so, the data is decoded and passed to the test harness. DRAM read and write are treated as simple array read and writes, completing instantly. Software register request to simple row can take many cycles to complete, so SimTop use a split-phase interface. Okay, in summary, use the DMA API to send the bulk data to FPGA to yield you high throughput. And you should use the share soft register. You should use the share register APIs to configure some basic interfaces or do some diagnostics. You can refer to the user guide for the definition of all the share registers. And you can use the soft register API to define your own configurations or check the status in your custom role or to do some statistics. You can use the CoSim framework to simulate your role on the behavior level. That's it. If you want any more information, you can go to the link. And if you have any question, you can send to catapult@microsoft.com. Thank you. Any questions?
I would have one. That communication library, if I heard correctly, is also available in a managed form. There is a managed library. Where can that be acquired?
Which management? Oh, you mean this?
Yeah, pretty much this one. Yeah, the very creative handles.
This management library?
No, the communication library.
Communication library.
Yeah, I heard that the communication library is also available in a managed form, so as .NET library.
This library is provided. And we have this is a DLL.
Yeah, I get that. It's just that that's a native library, written in C++ or something, I presume. But I heard that that's also available in a managed form, so as a .NET library, as a .NET DLL. Where is that available?
I don't know that. Maybe you need to ask Andrew. You can send email to the address to get an answer, because I have no idea of that. Sorry.
All right, thank you.
Zoltan, you can include that on your list of questions. We'll follow up with that.
Yeah, thank you.
Any other questions? Okay. Well, thank you, everybody. We appreciate your time this morning and your interest. We will be, again, as we did last week, posting the slides and the video out to the Catapult website. Once those are available, I will send out the information to the group. Next week, we're looking to our session on OpenCL. We'll be sending out invitations to that. If you have any questions, you can either send those to catapult@microsoft.com, or you can send those to me directly if you'd like. So if there's no further questions, I'll let everybody get on to their Friday. Have a great one. Thank you.
Thank you. Bye, everyone.